All right, let's talk about oxidation numbers, what they are, and how we assign them. To start off with, let's understand though what redox is. When we talk about redox reactions and starting to assign these oxidation numbers, we're talking about oxidation reduction reactions. So redox comes from shorthanding oxidation reduction. What we're looking at is the movement of electrons. So in some reactions, everything stays in the same oxidation state. So it has the same charge to it, or it has the same implied charge to it, all right? When we do electrochemistry, when we do a redox reaction, the electrons move around, okay? So when we think about oxidation, we're going to lose electrons, okay? Electrons are negative. So when we oxidize and we lose something that's negative, we get more positive, which is why we say it's an increase in the oxidation number. So it gets more positive. Okay, now when we do a reduction, we're going to gain electrons and we're going to decrease the oxidation number. Okay, so electrons, again, they're negative, and so when we gain them, we go down in number. So we're going to get more negative. All right. Now, when we talk about the oxidizing agent and the reducing agent, basically whatever process something undergoes, it is the opposite agent. So the oxidizing agent is the species reduced, and the reducing agent is the species oxidized. So whatever process something undergoes, it facilitates the opposite process in the other species. Now, for a redox reaction, you cannot have one without the other. If something is oxidized, something must be reduced. If something is reduced, something must be oxidized. The electrons have to come from somewhere, and the electrons have to go somewhere. They don't just disappear into the ether. Okay, so when we look at this, we're transferring or shifting electrons. So in this case, X is giving electrons to Y. X is losing electrons, it's oxidized, it is the reducing agent, and it will get more positive. Y is going to gain electrons, it is reduced, it's the oxidizing agent, and it will get more negative. Okay? Now we have this mnemonic oil rig. It stands for oxidation is loss, reduction is gain, and we're talking about loss and gain of electrons. Okay, so oxidation is lost, reduction is gain of electrons. So we can assign oxidation numbers. Now our oxidation numbers basically just kind of give us a bookkeeping number so that we can figure out where our electrons are moving. Now if we're using something that's an ion, it's easy. The oxidation number is just going to be the ion charge. But if we are dealing with something that's covalently bonded, where we don't have an ion, basically what it's going to be is a number that's equal to the number of charges the atom would have if the shared electrons were held more completely by the atom that attracts them more strongly. So atoms have different values of what we call electronegativity. The more electronegative something is, the more strongly it attracts electrons. And so the more electronegative it is, the more time electrons spend with that particular atom. And so the oxidation number is going to let us figure out if the electrons were completely transferred, okay, what would that number be? Okay, so we have some rules. If it's in its elemental form, the oxidation number is 0. If it's a monatomic ion, the oxidation number is the ion charge. If we're dealing with a neutral compound, our oxidation numbers will sum to 0. If we're dealing with an ion, our oxidation numbers will sum to the ion charge. For our metals in groups 1A and 2A, they always form their +1 or +2 ions, so those are going to be a +1 or a +2 for oxidation numbers. Hydrogen will have a +1 if it's with nonmetals. Fluorine will take a -1 with metals and boron. Fluorine is the most electronegative element. It will never have a positive oxidation number. Oxygen, you might encounter peroxides every once in a while. So if oxygen's in a peroxide, it's -1, but almost every other compound, it's -2. I would say 99% of the oxygens that you'll encounter, unless it's an oxygen molecule in O2, 99% of the oxygens you encounter in another compound are going to be a -2, except with fluorine. So oxygen is the second most electronegative element pretty much, and so but fluorine trumps it, so fluorine's always going to get that -1. So if you have oxygen and fluorine bonded together, fluorine gets the -1, and then we tweak oxygen. And then group 7A is interesting. It's -1 in combination with metals, non-metals, and other halogens lower in the group. So electronegativity gets lesser as we go down. And so fluorine is more electronegative than chlorine, so on and so forth. And so what ends up happening is if I have two halogens bonded together, the higher halogen will get the negative, and the lower halogen ends up having to be a positive. When we look at the periodic table, we get a range for some of our elements. So again, group 1A, group 2A, they're going to be a +1, they're going to be a +2, unless they're in their elemental form. Hydrogen has 1 valence electron. It can take 1 more. So hydrogen can actually be a +1 if it loses its electron, or it can actually be a -1 if it gains a second electron. It can go within that. Now, our group 3A, they'll do a +3 because those are the ions they form. When we get into group 4A, when we start looking at the nonmetals, we can get as high as +4 and as low as -4. Our group 4As have 4 valence electrons. So theoretically speaking, we could gain 4 more, or we could lose 4. And so we have that range. Our group 5A, we have 5 valence electrons. So theoretically, we could lose up to 5, and we can gain up to 3 more. Our group 6A have 6 valence electrons. So theoretically, we could lose up to 6 or gain up to 2. And then our group 7A, we can go between +7 and -1 because we can theoretically gain up to, or we can theoretically lose up to 7 and gain only 1. Okay, so because we're trying to, satisfy that octet. All right. So here we have just a little summary. We've got zinc and some hydrogen, so we can assign these oxidation numbers. So solid zinc would be in its natural elemental state, so it would have a 0. A hydrogen ion would have a +1. My zinc ion has a +2. And my hydrogen gas is its elemental form, so we get a 0. Now the thing with redox is once we start looking at redox, it's not enough just to balance the elements. We also have to balance the charge. And so when I look here, I have 0 charge here. Okay, each hydrogen is a +1, and there's 2 hydrogens there, so I have an overall +2. My zinc ion gives me a +2, and that hydrogen gives me a 0. So 0 + 2 is +2, 0 + 2 is +2, and 2 does indeed equal 2. Okay, so our charges also balance. Okay, so zinc, in this case, lost electrons. It went from 0 to +1, whoops, or 0 to +2, so it got more positive, and hydrogen gained electrons. It went from a +1 to a 0. Okay, so we're going to try some here. All right, our zinc chloride. So zinc chloride is an ionic compound, and it's ZnCl2. Okay, so it's an ionic compound, which means that our oxidation numbers are just simply going to be the ion charge. So chloride is always a -1, and zinc is a +2. And we get our 0, because I take +2 + 2 times -1 does give me 0. Okay, now let's try a covalent one, sulfur trioxide. Okay, so oxygen has a rule from that slide that I showed you with rules. The rule with oxygen is that -2. Okay, sulfur doesn't have a rule, so we're going to have to balance out the charges to figure out what sulfur is. So we only have 1 sulfur. Okay, so it's just like we did the charge balancing for ionic compounds. So I have 1 sulfur with some oxidation number times 3 oxygens with an oxidation number of -2 for each of them, and an overall 0. So what oxidation number does sulfur have to get this to equal out to 0? Sulfur is going to end up needing a +6. Okay? All right, nitric acid. Let's see here. Put that, there we go. Okay. All right, so our rule for oxygen tells us that oxygen is -2. We had a rule for hydrogen that ends up being +1. So like with the solubility rules, it's a really good idea to print out that oxidation number chart and refer to it as we're doing this. That way you can follow along and start learning the rules for assigning these. All right, so when I look here and I try to figure out what nitrogen is, again, I need to have everything come out to 0 because this is neutral. So I have a +1 plus some number of nitrogen at some charge plus 3 oxygens at a -2 oxidation number. Okay, and so to get this to fill in, I have 1 nitrogen, whoops, I need a +5. So nitrogen takes on a +5. Okay? All right, so here's a few more. Try to give these a shot. Okay, these I put the formula instead of the name. So try these before you check the answers. Okay, so we've got this scandium oxide. It's ionic, so we just do our ion. So scandium ends up being a +3, and oxygen is the -2. Okay. All right, I've got this gallium chloride. It's also ionic, so that one's nice. So gallium ends up a +3, and chloride -1. All right, now I have this hydrogen phosphate ion. So remember that if we have an ion, the sum of the oxidation numbers has to equal -2. So when you assigned these, hopefully you had it equal -2 instead of 0. So in this situation, what you will get is hydrogen will have an oxidation number of +1. Phosphorus will have an oxidation number of +5. And oxygen will have an oxidation number of -2. Okay? All right. Now, we've got this iodine trifluoride, so 2 halogens together. So remember, halogens can have an oxidation number all the way up to +7 or just a -1. Now, fluorine is that most electronegative element, so fluorine's always going to get that -1, especially when it's bonded to other halogens. So fluorine's going to take the -1, and so we only have iodine and fluorine in this compound, so iodine is going to have to take on a positive oxidation number. So our iodine, when you balance it all out, has an oxidation number of +3, and fluorine has an oxidation number of -1. Okay, so that's how we determine those. All right, now let's step it up a notch. We're going to try to figure out what the oxidized and reduced species are and the oxidizing agent and reducing agent. Remember, the agent is just the opposite of whatever process it undergoes. Okay, so let's see here. I think for these, I'm going to assign the oxidation numbers above each thing in red. All right, aluminum's in its natural state. It gets a 0. For our sulfuric acid, hydrogen is a +1. Oxygen's the -2, sulfur gets a +6. At the backside, aluminum sulfate, aluminum's a +3. This is still a +6, this is still a -2. Okay, now when you have a polyatomic ion like this, like the sulfate, that you see it on both sides, guaranteed the oxidation number is going to be the same on both sides like that. And then our hydrogen here is a 0 because it's in its natural elemental state. Okay, so what happened? Aluminum, okay, went from a 0 to a +3. And hydrogen went from a +1 to a 0. So if I'm going from a 0 to a +3, am I getting more positive or more negative? I'm getting more positive, which means I'm getting rid of negative charges. So aluminum was oxidized. And if it's oxidized, it means it's the reducing agent. Okay. Hydrogen went from a +1 to a 0, so it started to get more negative, which means it gained electrons, so it was reduced, which means it's the oxidizing agent. Okay. All right. Now we've got some lead-2 oxide, some carbon monoxide going to lead and carbon dioxide. All right, so our lead-2 oxide, our oxygen's a -2, our lead's a +2. Now in my carbon monoxide, again, oxygen gets that -2, which means that carbon has to be a +2, lead's a 0, and then carbon dioxide, we still have that -2, and then there's 2 of them, which means the carbon's a +4. All right, so in this situation, lead changed oxidation numbers, carbon changed oxidation numbers, but oxygen did not. So oxygen didn't undergo any redox processes, but lead and carbon did. All right, so let's take a look at the lead. Lead went from +2 to 0, okay? Carbon went from +2 to +4. Okay, what happened here? So lead, I went from +2 to 0. Did I get more positive or more negative? I got more negative. So lead was reduced, which means it was the oxidizing agent. Okay, carbon went from +2 to +4. It got more positive, so it's oxidized, and it is the reducing agent. Okay, all right, now here's 2 more. I would like you to try these on your own before I give you the answers. Okay, so hopefully you got these. So natural state, 0 and 0, -2, +1. All right, so hydrogen, it went from 0 to +1. Oxygen, 0 to -2. Okay, so that means that hydrogen was oxidized and the reducing agent. And then oxygen was reduced and the oxidizing agent. Okay, all right. And then our last one, iron and chlorine are in their natural states on the reactant side, and they're in an ionic compound on the product side, -1. There's 3 of them for an overall -3, so this is why this is a +3. That's iron 3 chloride. So iron went from a 0 to a +3, and then chlorine went from a 0 to a -1. Okay, so iron went from a 0 to a +3, which means it got more positive, so it was oxidized. So it's the reducing agent. And then chlorine went from 0 to -1, so it got more negative, so it was reduced, and is the oxidizing agent. Okay, so these take some practice. All right, so you'll have to go through these and practice them.